Let's look at this question to find out the direction of the magnetic field at P. You have two loops and the current is shown. So each of the loops will produce magnetic field, and we want to know what's the magnetic field at point P. So last time we learned that whenever there is a current, the current produces magnetic field. Okay, so you have a loop carrying some current. So this is a loop carrying current in, from your perspective, it's clockwise. Because of the current, there would be magnetic field around it. Okay, and we don't care about other locations. We only care about at the center, because other locations it's a bit complicated to find the magnetic field. So to find the magnetic field at the center, we use right hand rule. Okay, so the right hand rule is you point your thumb towards the direction of current. Okay, so current is going that way. Okay, you point your thumb and then wrap your fingers around the loop. Okay, around the wire like that. You do like that and then see which way your fingers are pointing at the point where you are finding the magnetic field. So I'm finding the magnetic field at the center, so my fingers are pointing that way. Okay, into the page or into the screen. Okay, so that means the magnetic field is going that way. Okay, so in this loop there is some magnetic field going through the center, and there is also some magnetic field going through the center of this. So what would be the addition of that magnetic field and that magnetic field at the point P? So this is the side view and this is the front view. Okay, if you look from the front, so in this one, so my current is just opposite to that one. So yeah, so it's like that. So this one is like that. It's going counterclockwise. Okay, right? This current is going counterclockwise, right? Opposite to the clockwise direction. So counterclockwise. And if you look from this perspective, what you will see is on the top, okay, on the top current is coming out. Okay, you see, if you look at this perspective, current is coming out on the top and current is going in on the bottom. If you cross this and look at the cross section, you will see current coming out from the top. That's what you see, right? Current is going that way, so that means if you see from here, current would be coming out, and on the bottom current would be going in. That's what you have here. Same thing with that one. So if you look the cross section, current would be coming out on this part, top part, current would be going in at that part. Okay, this current would be going in and that would be coming out. So what's the net current at point P? Or not current, magnetic field. We just want to find the direction. What's the direction? To the right, up, right, left, down, out of page, into page. There's no magnetic field or none of the above. So you're saying out or to the left?
No,
to the right. Okay, so who else say to the left? What's your answer? Come up with the answer. Okay, everyone write your answer on your notebook or so what's your answer? Is it to the right or to the left or to the right? Some other are still thinking. Let's use right hand rule. So imagine that you are looking at this one. Point your thumb towards the loop. Okay. So you have a loop like this. Point your finger. My current is opposite direction, so I will. So this is the loop. So current is going counterclockwise. Okay. So you point your thumb along the direction of the current, and then wrap your fingers around this loop. Okay, just like I did. Wrap finger around that loop. Which way would be your fingers pointing at that point? Would it point to the left or to the right? In that you're holding this loop with your fingers. Which way my fingers are pointing? To the left or to the right? To the right. Right? So that means the magnetic field of that one is going to the right. Likewise, you do the same thing with this one. Okay? Hold this loop with your fingers, pointing your thumb down. Your fingers are pointing to the right. So both have the magnetic field in the right direction. So you need to be very clear with this one, because we'll be using this very frequently, because there are lots of right hand rule in this chapter. So this one, magnetic field, for this one magnetic field is pointing to the right. Okay, so call that B1. And for this one also, magnetic field is pointing to the right. Okay. And then at that point, both are pointing to the right. That means the net magnetic field would be to the right. That means A would be the right answer. Any question? Still not sure how to find the direction of magnetic field? Is it clear? Okay, good. If you still have question, let me know. Okay, so this is to find the magnetic field. Okay, that's the one right hand rule. Now next right hand rule is to find the force. So let's look at this question. We have two wires carrying current in the given directions. So the question is, what is the direction of the magnetic force that wire 1 exerts on wire 2? So what would be the direction of the force felt by this wire due to the magnetic field of that wire? Okay, so write your answer on your notebook. So what's your answer? Let's see, where is it? Here. Tell me an answer. Is the force on wire 2 due to wire 1 to the right, to the up, left? So you are saying up. Okay, one answer is up. Any other answer, or do you agree with Alex?
I agree with Alex again.
Okay. Okay, so we got 2 answers. So let's see if that's the right one. So first we need to think about what causes the force. The force is caused by magnetic field. Okay, so that means we need to think about the direction of the magnetic field produced by this one. So this produces magnetic field B. And what's the direction of the magnetic field produced by that? Again, use right hand rule. Okay. Yeah, so that's the current. Point your thumb towards the current and wrap your fingers around this. And then we want to find the magnetic field at this point, because we want to find the force on this one. So what's the magnetic field at that point? So at that point, see the finger. So finger is coming out of the page. Okay, it's coming out. Okay, so out is represented by dot. Circle with the dot. So that's the magnetic field due to wire 1. Okay, that's B due to I1, and that magnetic field causes the force, and the direction of force is given by right hand rule again. So F is V, not V, I L B sine theta. So the direction of this force is given by using the right hand rule again. This is different kind of right hand rule. So point your fingers towards I and then curl towards B, and the thumb will give you the direction of force. Okay, so let's look at that. So I is going to the right, so that's I. Okay, and then B is coming out. Okay, that's B, and then use the right hand rule. So point your fingers towards I, okay, and then curl towards B, not like that, but like that. Okay, so your thumb is pointing down. So that means the force is down. That's the force on wire 2 due to wire 1. Yes.
I thought you were asking before on wire 2 on wire 1.
Oh, is it wire 2? Okay, maybe I read the question incorrect. Okay, let's see. I may be wrong, I don't know. So let's see. What is the magnetic force that wire 1 exerts on wire 2? So that means force on wire 2. So yeah, so force on wire 2. So force is pointing down. Now I will ask you guys, oops, let's see. So what's the force of wire 2 on wire 1? So force on 1 due to I2. You're saying up? Okay. So we have 30 seconds to come up with the answer. So first you need to think about what causes that force. What produces the force on wire 1? The force is caused by the magnetic field of this wire. Okay, this wire produces magnetic field B, and that force causes the force. So that's why you need to first find what's the direction of this B at the point where we want to find the force. So we want to find the force here. So think about the direction of the magnetic field at that point. So use right hand rule, point your fingers towards the direction of the current. Current is going to the right. Okay. Thumb towards the current, and then wrap your fingers around, and then see which way your fingers are pointing at that point. It's coming out, right? So that means the magnetic field is coming out at that point. Coming out, coming out, coming out, coming out. Okay, that's the magnetic field. And our current is going that way. So our current is going that way, and magnetic field is out. Which way would be the force? Right hand rule. So point your fingers towards the current and curl towards the magnetic field. So magnetic field is out, thumb is up, right? So the force is up. So that's the force. So this will feel, this wire will feel the force in the upward direction. Sometimes people like to use another kind of right hand rule. Okay, I will also tell you the other one if you don't like the curling one. For the force, to find the force, you can use this one also. So point your finger towards the direction of motion, or either velocity or current. Okay, fingers either V or I, anything that is moving, point your finger, this finger, index finger, towards that. Okay. And your middle finger point towards the magnetic field. Okay. B, and then your thumb would be the force. Okay, so just like finger is direction of motion, middle finger goes to the magnetic field, and thumb would be force. Okay, that's also the right hand rule. So you can use this one or use the curl, whichever you want. Okay. Let's see if I have any other question. Okay. Those two questions should give you a good idea about the things we have done so far about the direction. Now let's talk about what happens if we move a conductor in a magnetic field. So let's say we have a magnetic field. This means the magnetic field is pointing into the board or into the screen. Okay, so this is motion of a conductor in a magnetic field. Let's say this is a uniform magnetic field. Okay, magnetic field that is not changing, a constant magnetic field, a uniform. So we have a conductor, and this conductor is moving either to the left or to the right, whichever we want. So let's say it's moving to the left, okay, at some speed or velocity v. So what happens to the protons in the conductor? Basically, when we deal with the current, we talk about the motion of positive charge. Okay, that's the convention. That's why it's called conventional current. So we want to know about what happens to the positive charge, how the positive charge moves. So assume that there are lots of positive charge in this conductor, and out of trillions of positive charges, consider one positive charge. So what happens to that positive charge when we are moving the rod to the left? There is a magnetic field pointing into the page, and in the magnetic field the rod is moving to the left, and the rod has trillions of positive charges. So out of trillions, what happens to that particular one? Will that feel force? Yeah, so it will feel some force. Okay, let's wait for a second which way it would be pushed. It will feel some force. We know whenever a charge moves in magnetic field, it will feel some force. And which way it feels the force? So use this. That one to the direction of the motion or direction of velocity. Okay, and this one to the magnetic field. Magnetic field is not out, so I need to do like this. Okay, so my finger to the motion, my middle finger goes to magnetic field into the page, and my thumb is the force, so down. Okay, so the force, this feels the force in the downward direction. I can also use curl. Okay, so point your fingers to the speed or velocity and curl towards the magnetic field. Magnetic field is pointing into the board, so curl towards the magnetic field like this, thumb is pointing down. So this feels the force in the downward direction. So we have negative as well as positive here, negative as well as positive. So all the positive charges would be pushed down, leaving behind negative charges on the top. Okay, we found that the positive charge feels the force in the downward direction, so that means positive charges would be pushed down, will go down, and the negative charges are pushed up, or you can say the positive charge are left behind on the top. So we have some positive down and some negative up. Whenever we have separation of charge like that, what happens? We can have two things. This is from the previous chapter. We have bunch of positive charge on one side and bunch of negative on other side. What's the consequence of that? Not magnetize. So before magnetism, it's a kind of dipole. So yeah. So what is the physical quantity that is produced? When you have bunch of positive and bunch of negative, we have done lots of examples like this. One example is capacitor. So in capacitor plates, we have bunch of positive on one plate and bunch of negatives on other plate. There may not be current, but there are definitely two things involved when you have separation of charge. Electric field, yes, that's right. What else? This is at one potential, higher. Whenever you have positive charges, it's said to be at higher potential. Okay, this is at one potential. This is at another potential, lower potential. So, we have potential difference, okay, delta V. Like in battery, this battery has potential difference of 1.5. The D cell battery has 1.5 volts potential difference. The reason we have potential difference is one side is at higher potential and other side is at lower potential. That causes the potential difference. Okay. So, we have potential difference across the conductor. As well as there is electric field. So, like we discussed last time, electric field and potential difference are equivalent. When there is one, there is always the other one also. So, there is this delta V potential difference, and when there is potential difference, there is also electric field. Okay, and electric field always goes from positive to negative. So, we have two things here, delta V and E. So, what is the relationship between delta V and E? We already talked about this last time. What formula relates these two things? Do you guys remember? I don't expect you to memorize, but if you remember, you can tell me. E is given by, we have the relationship between E and delta V. E is given by delta V over D. Okay, that's the relationship. That's why if there is delta V, there is E. If there is E, there is delta V. Because there is separation of charge here, so we have delta V here, and that means there is also E, and E always points from positive to negative. Okay, and this delta V is called motional EMF. Okay, motional EMF. EMF is same as potential difference. Okay, EMF. Why? Now, how to get rid of that? So, this is same as potential difference. Okay. So, we have potential difference, which is called motional EMF. It is called motional EMF because it is produced by the motion of that conductor. That's why it's called motional EMF. So, we want to get a expression for this delta V, motional EMF. What is the EMF produced? How much EMF is produced in this conductor? Okay. So, this positive charge, let's consider this positive charge. This positive charge will feel two forces. Can you guys think of what are those two forces? So, we have this rod in a magnetic field. Okay. This one feels two forces. What's the first force? What pushes the charge downward? Magnetic field, yes. So, the magnetic field pushes this positive down, which we called magnetic force. Let's call that F sub B. That's the force due to the magnetic field. Okay. Do you guys remember the formula of the force on a charge due to magnetic field? We talked about that last time. When a charge is moving in magnetic field at some velocity, what's the force on that? This feels some force. The force is given by Q V B sine theta. Okay, so that's the force due to the magnetic field. and this sine theta is angle between V and B. What's the angle between V and B? 90 degrees. So V is that way, B is down 90 degrees, right? So the angle is 90 degrees, and sine of 90 degrees is 1. So that means this force, which is due to the magnetic field, is QVB. Okay, this is 1. So that's the one force, okay, force 1, and this also feels another force. Can you guys guess what that force is? That force comes from this electric field. Okay, so we have positive charges pushes down and negative charges pushed up, and we have this electric field. So we have electric field which is always pointing towards the negative, going from positive to negative. So this is electric field, and that electric field also causes the force. So this will feel some force due to that electric field, which is given by, do you guys remember? When you place a positive charge in electric field like this, okay, there is some electric field, you put a proton. Which way will the proton be pushed? Down or up? Down, because the positive charges push the positive down. So there is, let's see, is it down? Yeah, down. In this, sorry, I gave the, yeah, in this case it's down, but here we are talking about this one. Okay, in this our conductor, which way will be the force? Let me erase that. So in our conductor, which way will be the force on the positive due to the electric field? Up, right? So that will be up, because this is pushed away by these positive charges and pulled by these negative charges. So we'll have Fe in the upward direction. So we have two forces. Okay, let me just write the forces. One is down due to the magnetic force, and there is up force due to the electric field, Fb, Fe. Fe is given by, what is that? Force on a charge due to electric field, Q times electric field, right? That's what you got in the previous chapter. Okay, and at some point these two forces will be equal. Okay, they will not be equal in the beginning, but as more and more charges accumulate, the electric field will increase. It will increase, and then at some point it will be in this charge would be in equilibrium, meaning the upward force and downward force would be equal. So at equilibrium, Fb would be equal to Fe. Okay, and then at equilibrium there won't be any more movement of the charge. The charge won't be separated anymore. So you will have maximum potential difference at that point. So at equilibrium, Fb is QVB, Fe is QE. Okay, so this one is that, and this one is that. So cancel Q and Q. Then we will have B is equal to E over V, okay, velocity. So that's the relationship between V and B for the equilibrium. Okay. But here we want to find, okay, we can also write this as E is equal to VB, same thing by rearranging the things. But here our purpose is to find delta V. Okay, how much potential difference would be there across the top and bottom of this conductor. We want to find this delta V, potential difference, or EMF. And we know its EMF is, we know E is delta V over D. That means delta V would be E times D. Okay. E is that VB, and D is this distance, okay, which is the length of the rod. So D is L. So that means the potential difference produced in this rod or this conductor is VBL. Okay, so this is the motional EMF, or you can also say motional potential difference, which is the potential difference due to the motion of the conductor in a magnetic field. This is due to motion of the conductor. Okay. This effect is also called Hall effect. Whenever there is separation of charge like this effect is called Hall effect. Producing motional EMF is called Hall effect. Okay. Any question on this one? This is the principle on basis of which there are lots of sensors developed, like the sensor we used at airport, the metal detector, that's based on this principle, and there are other different principles that are based on this. We'll talk about that later. Okay, so let's look at a problem. If you don't understand, you guys need to tell me what you didn't understand, okay? Because I don't know, I don't have magic to know whether you understood or not. So you need to tell me if you don't understand something. Okay, so let's look at this problem. We have this U-shaped rail and this U-shaped rail is in a magnetic field. So this is the rail U-shaped, and this is connected to a resistor which has 1.2 ohms, and it's in this magnetic field which is 2.2 Tesla, and this magnetic field is pointing into the page or into the screen. Okay, that's the magnetic field. and there is a rod, this conducting rod, and its length is about 10 centimeters. Okay, so that's the length of this rod. It's a little bit above, more than 10 centimeters, but we consider this to be 10 centimeters. So it is moved to the right or pulled to the right at 2.0 centimeters per second. So when we pull this to the right, because this is a conductor, so this will produce EMF, it will produce Hall effect, or it would produce motional EMF. So can you guys tell me which way would the positive charge move? Let's say you have a positive charge here. When I pull this to the right, pull the rod to the right, which way would the positive charge move? Will it move up or down? Right hand rule. With your finger to the motion. Magnetic field, middle finger, so down. So that's the magnetic field, that's the motion, thumb is pointing up. So the current would be moving up. So the charge would be moving up, means the current would be up. Okay. And because this is touched to this circuit, this works as a circuit. Okay. It will not just accumulate the charge on the top here, because this is connected to this bar. So the positive you accumulate here previously would circulate in this circuit. So that would be the direction of the current. Okay. So now you have a circuit. So assume that you have a battery here. Okay. So this works as a battery with positive charge here and negative charge here. So there will be current in this direction. And that current is what we call induced current. Okay. So that's what we want to find. So we want to find I induced, because there is EMF produced by this that works as a battery. So this works as a battery, it produces EMF, induced EMF. So there is induced current because of that. Now we want to find that. We know from Ohm's law, delta V is, what's the Ohm's law? I times R. If I want to find I, then I get delta V and divide that by R. And we just derived an equation for this delta V, which is EMF. What is that? In the previous discussion, we got the expression for that. V, yes, V, BL. So do not be confused this V and this V. Okay, this is the potential difference or EMF. This V, small v, is speed or velocity. Okay, so always be careful with this V and this V. That's the potential difference. That's the speed. So that's delta V over R. So V is, we are moving at 2.0 centimeters per second. So change that to meters. Okay, that's the speed. Magnetic field, we are using 2.2 Tesla. Length of that rod, 10 centimeters. So 10 times 10 to negative 2 is in meters. And the resistance in this circuit is 1.2. Okay, so let's find that out. I didn't have the calculator. So let's see what you get. .7 times 10 to negative 3 current is amperes. Induced current is that So the second part of the question is, now we know that when you move a rod in magnetic field, the rod feels some force. We already talked about that. Which way does the magnetic field exert the force on the rod? Should I erase that? Let me erase that. Oops. So this rod will feel some force because it's moving in the direction of magnetic field. Now you use the right hand rule and tell me which way the rod feels the force. Still be up. Current, because it's a current. So this is a, that's a very good question. Okay, so you have a current, okay, the current is moving up. You have a wire, and the wire is in magnetic field. So which way is the force felt by that current? To the right. Okay, let's see. So magnetic field pointing into the page, okay, and then that's the direction of current. Magnetic field, that's the force, right? So to the left. So force is to the left. Now this rod feels the force. We are moving the rod to the right, but it will feel this force. This force acts as a resistance. Okay, so to move this at constant speed, we need to overcome that force. Okay, that's what we want to find here. So what force will keep the rod in a constant speed? So in order to overcome that, we need to apply same amount of force in this direction. Okay, so this force is to overcome that force. So that's what we want to find, how much force we need to apply to overcome that force, and it is given by, okay, we'll do this next time. Okay, we are out of time, so we'll keep this working on this next time.
That's the ILD.
Yes.